Question 2, and we're on to centres of mass. We've got a uniform lamina, so some sort of two-dimensional object, and it's formed by removing a triangle from a square. We're also given the side lengths, and so we're ready to get started on this. So let's just scroll down the page and create ourselves a new picture. So I'm thinking about this like a compound area question, where I want to first of all think about the square, and from the square I want to subtract the triangle, because that's then going to leave me with this sort of weird shape that I've got left over. So there are lots of things that I need to know here. So first of all, that this is 2a by 2a. I need to work out what the area of the first shape is, 2a times 2a, so that's going to be 4a squared, because I'm not given masses here, so I assume that the area of the shape is its mass. And the triangle section, well, the easiest way to think about this is the triangle just formed 1/4 of the whole square, so the mass of this one quickly can come out to be a squared. And then obviously if I've got 4a squared of the mass of the first object and a squared of the mass of the second, then the mass of the final object is going to be 3a squared. Now I'm asked to show that the centre of mass is somewhere from O, and O is the point directly in the centre of my square. So what I'm going to do now is I'm going to set up a coordinate system where I'm taking the origin, or the centre of my coordinate system, to be the centre of my square. That allows me to say that the centre of mass of the square is going to be at the coordinate 0, 0. Now for the centre of mass of a triangle, I know that all I need to do is to add the vertices together and divide by 3. So using my coordinate system, this point here would be 0, 0, because it was at the centre of the square. And thinking in terms of distances, in order to get to the vertex in the top right hand corner, I needed to go A across and A up, so that's going to give me a vertex of A, A. And in a similar vein, this one would be minus A, A. So where I'm now looking to find the coordinates for the centre of mass, what I want to do is 1/3 of minus A, A plus A, A plus 0, 0. It's really easy to see, and as we would expect, the x-coordinate, so that along the top line, the x-coordinate is going to be 0, which we would expect because this is a symmetric shape, so its centre of mass has to lie on its axis of symmetry, so this point here is 0. And in the second part I've got A plus A, which is 2A divided by 3, so that's 2/3 of A. And that's going to be equal to 3a lots of the centre of mass of the whole system, which is x bar y bar. I can notice here that I can divide through by a squared, and what I'm going to end up with is, well, the first calculation here is just going to be 4 multiplied by 0 and 0, so that gives me nothing at all. I've cancelled out the a squared, so the next bit I'm going to see is that I've got 0 and minus 2/3 of a, and that's going to be equal to 3 lots of x bar y bar. Now if I divide by 3, I've got 0 and minus 2 over 9 a as my coordinates, x bar y bar. So that's the centre of mass of the new system. Now you may be thinking at this point, why am I bothering to do both the x coordinate and the y coordinate? The easy answer to that is that it's no skin off my nose to be able to do both at the same time, and actually in some questions where you are required to find for part A the distance in the horizontal direction and for part B the distance in the vertical direction, it just makes complete sense to always use the same method and then go through a process at the end where we interpret our answer. So what does this mean? It means that the y coordinate was 2 below where we started, so I'm just going to make clear here that the centre of mass, or COM, is 2 over 9a below the origin. Okay, and that's my answer for part A. The second part of this question, a mass of m, we're now told that the lamina has a mass of m, and there's a particle of mass km which is attached to the lamina at D. The system S, to form the system S, which is then freely suspended from the point A to hang in equilibrium with O to A to the vertical. So again we go back and we think, right, so we're going to hang a particle on here. We had our centre of mass of the whole system as being somewhere about here. We're suspending from this point, and we know that it then hangs in equilibrium. So moving to what this would look like, let's try and draw this out again. So this is going to be my point A, where O to A is to the vertical. Now I knew on my previous diagram that this was at 90 degrees, so I've got this straight line moving out here to my point, which is at D, and at point D I've got this mass of km. Finishing off the drawing of my picture, it's going to look something like this, where the centre of mass of the whole system was somewhere here, where we knew this distance here was 2 over 9a, and we knew that the mass of this was going to be mg. So what I need to now go about doing is working out a value for k. Now, in order to do this, I need to be thinking about taking moments, because the system is in equilibrium. I know that I can choose a point, take moments, and I should get a zero sum. So what I'm going to do is I'm going to take moments about the point A. So I need to be thinking about the perpendicular distance that these forces are acting from A. So this one's fairly straightforward, because going back to my original diagram, I'm thinking here that this is going to be A and this is going to be A. So to find the length of the longest side, we're just doing Pythagoras. So I've got A squared plus A squared square rooted, which comes out to be A lots of the square root of 2. So my distance in here is A lots of the square root of 2. Now slightly harder is my other distance, which is just this one across the bottom here, but we should then start to realize certain things about this system. So if I were to continue, and on my poor diagram it doesn't quite work out very well, but if I was to continue this line vertically downwards, it should meet up with this vertex in the corner. We knew that the angle in here was 45 degrees because of how the square is constructed, so that tells us that the angle here must also be 45 degrees. Now I can use basic trigonometry to work out the length of the perpendicular distance from this line of action, and that is going to be 2 over 9a sine 45. Well, we should know that sine 45 can be written as 1 over the square root of 2, or root 2 over 2, and at this point we're ready to go. So now I can make my moments at A. And remember, we're only ever interested in the perpendicular distance from our point that we're taking moments about, so that's why we've gone about calculating these. So moments at A, so we want our clockwise moments to equal our anti-clockwise moments. All the moments that are acting clockwise, that's this one here, which is going to be the force, which is mg, multiplied by the distance, which we calculated to be 2 over 9a sine 45, which was 1 over root 2, is going to be my anti-clockwise moments, which were kmg multiplied by a root 2. I can cancel mg from both equations, so my next line will divide through by mg, and at the same time I'm also going to multiply through by the square root of 2. I can also divide through by a, so quite a lot's going to change from one line to the next. So the mg's are going to go. I'm still going to be left with this 2 over 9. I've divided out the a and I've multiplied up by root 2. And on this side I'm going to have k, which hasn't gone anywhere. I've divided the mg's, I've divided the a, and I've multiplied by root 2. And obviously root 2 times by 2 is 2. So now just quickly to finish off, divide both sides by 2, and I've got 1/9 is equal to k.